Good morning. Plasma. What is plasma? Well, if you look at a galactic scale, we have massive amounts, like our galaxy, we have massive amounts of plasma going between the stars. It's they consider it positive and negative radiation. Particles that were blown apart from the atom, so we have electrons and protons floating all over space, right? I mean all over space. And we have all these magnetic fields between the stars and the planets and all this other stuff, right? And our galaxy, well, floats around a core with all this plasma and all these stars made out of plasma, right? Or vastly made out of plasma. And these stars are constantly exposing more and more radiation, more and more plasma all through the emptiness of space, right? In the forms of light and electrons and protons, right? And all these stars float through the plasma. Now, Maxwell put it pretty simple, but he wasn't looking at entire galaxies at the time, but his math works fantastic, especially when Lorentz throws in his own additions, because he was looking for the ether. Maxwell was looking at electromagnetism. Lorentz says, ooh, that's a good place to start, but he was looking for an ether. He thought it was a fluid. But let's just say it's magnetism, okay? And the magnetic pull between positive and negative charges is brutal. Short range, but brutal. And way stronger than what we call gravity. And a star is basically a big pile of raw mass that has a massive magnetic field. And the reason being is it's largely plasma, all right? Largely unexposed, or exposed, largely exposed protons, neutrons, or whatever we want to call it. It's plasma, right? With that in mind, when you look at a galaxy, it looks like a fog, like a storm almost, right? And when you recognize that all those stars are light, they're big stars. So that fog is made out of a dense cloud of electromagnetic charges, all right? It's not mass that we call it. It's not neutralized, right? So it's got a strong magnetic field. And that magnetic field is actually what we call plasma, all right? We look at the plasma and the flow and the control and all of that stuff, and it's all the electromagnetic field, and it's all controlled by the rotation and the mass and all this other stuff of the stars. And when you bring that down to our solar system, what we have is a massive plasma furnace controlling the solar system, which includes its own magnetic field and its own magnetic plasma, and it drags the plasma and all the planets with it, because to go against the flow of that plasma is to cause what time dilation calls velocity, all right, is going against the flow of that plasma, all right? And that plasma is what we call magnetism, and it's the magnetic field, or the flow of the magnetic field. And we can see it and measure it and all that other stuff. We've been doing it for years. I'm about ready to lose a dog. She just went off into the woods. All right, I gotta get going. But so when we scale that down to size again, what we have is atoms that surround themselves with a strong magnetic field. It goes 1 divided by r squared, right? And at an atomic scale, that 1 divided by r is brutal. So that first atomic layer around an atom is absolutely unstoppable. But when you look at a molecule, what you have is a stack of shared plasma, all right, that we call electrons. It's got a shared field of plasma that we call electrons. And then around that, extending out, is more and more plasma, all right? I'll get back to you.